So, hey everyone, hope everybody's doing good. I have my micro teaching on a plant called the Mimosa pudica, and it's actually it was an everyday phenomenon for me in my household because we had it in our backyard, and it did a special thing every time anybody got close to it, and that's what I'm gonna talk about in the presentation. And The question I wanted to start off with was, what are some ways that plants adapt to the environment? And I was wondering if anybody could answer that question.
Um, they go to get more sun.
Hmm. That's one of the ways that they're actually capable of doing a lot of things. For one of them, it can do toxic sap, and there's some species of plants where if an animal gets close to it, it starts letting off a gooey sap to deter insects from like, eating it or getting close to it. And like you said, it responds to light. So if you were to put a plant next to a window, and it would try to move a little close to the window so you get sunlight. Another thing is that they are capable of sensing gravity, so that's why their roots always grow downwards because they can sort of feel where the gravitational pull is. And another thing that a lot of people don't know is that they actually communicate through the air. Um, they are capable of sending chemicals in the air to talk to one another. It's like something that you can't really see, but it happens. But these are all important ways they adapt. And I think it's important to sort of teach these things to kids because early on they sort of see plants as like things that don't exist just because they don't have characteristics that mammals have. But yeah, they're just capable of doing this and other things. And another thing that they're capable of is respond to touch. Does anyone know the plant that can respond to touch?
I do.
The Go for it, Don.
The Venus flytrap.
Yeah, that's actually the most common one is the Venus flytrap. As you guys know, it's usually for flies and insects. And the way that it works is that it has these little triggers inside the mouth. And whenever a insect goes inside, the little trigger sense it. But the thing about it is that it only it only closes whenever two triggers are pressed because it takes into consideration the amount of, I guess, the mass of it because it doesn't want to waste its energy on just a small insect tries to go for something big because if they waste their energy on something that they're not really gonna you know really getting a lot of food from, then there's no point. So they try to get their triggers, two triggers at least, and then once it closes, it releases a sort of a wax, and then the more it moves, the easier it is for the Venus to uh, um, to eat it. And another plant that a lot of people don't know is a plant called the Mimosa pudica, which has a lot of nicknames. I'm not sure if you guys ever heard of the sensitive plant, the humble plant, the shame plant, or the touch me not plant. Anybody hear about that before?
No, but
Uh,
I know that fern. It looks like a fern to me. I like
Hmm.
that.
Yeah, it actually comes in a variety. All of these, there's like large varieties of these. This is the fern, and they also comes in little trees, and it just comes in different forms. But it sort of all does the same thing. And the way it works is that it responds to touch by closing the little leaflets. They're going to show some gifs on how that works.
Oh, that's cool.
That's sweet. Nice.
This is a baby one. Yeah, but we actually, as I said, this is how it works. The little leaflets close whenever it senses touch. But I consider this an everyday phenomenon just because we used to have this in our backyard, and we have a pair of dogs, right? And whenever the dogs would get close to it and like put their nose on and try to smell it, it just closes them. And I would just always be surprised, and I always found it surprising too. And I just never looked into it. I always thought it was sort of similar to the Venus, where it has some sort of like trigger hairs or something that closes it up. But it turns out it's not that way. But this this phenomenon works differently from the Venus. It doesn't have trigger cells, so it does it through a different way. So what it's capable of doing is doing seismonastic movement, which is movement brought by the mechanica stimuli. And what that means is that it moves when something touches it, whether that be, a dog, raindrops, wind, and just anything that touches it, really insects. And the reason why this plant in particular does it is because it wants to deter away anything that tries to eat it, like sort of almost scare them off, like it did my dogs whenever try to smell it. But yeah, its purpose is to frighten whatever tries to touch it. And the way that it does it is that it has receptor cells which detect the touch. And as you guys see in the pictures, like these tiny little red cells, and they sense touch. And as soon as you touch it, it sends an electrical pulse through the leaflet and the branch. And this just tells the plant that, hey, something came in contact with you, which is something that not lots of other plants have, which makes this plant unique. So another way to put it is they have receptor cells which signal a warning sign, and then it creates a dropping movement, which then in turn gives the little folding movement, which is the little leaflets closing. And the way that the leaflets actually close is because the plant cells are, well, this one in particular is full of large fluid, which is water, and the vacuole. And since it's full of it, the way it closes is because when it's full of it, it has turgor pressure, which means that the cell expands and is rock hard, and it doesn't bend in any way or turn any smaller. And it turns small once the water is taken away. So there's a chemical that gets sent. So once the plant finds out that something touched it, it sends a signal throughout the plant, which then in turn sends back a chemical, which then makes the cells lose the water, which makes it shrivel up, which then in turn makes the leaflets close. So it takes a pretty long time for it to expand. Once it loses the water, it takes up from anywhere from 15 minutes to a couple hours to expand. But in order for it to turn small, it happens really fast, as you guys saw. It's like unbelievably fast that it sends the signal so quickly, and then there's a response that's even quicker. So just a little recap on that is that the cells detect a touch, which then cause the transmit of signals, and then chemicals are sent to the cells, which causes the turgor pressure to close up. So once it loses the turgor pressure, that's when you see the cells shrivel up, which then causes the actual plant to fold. And something interesting I found when I was actually finding out about the plant is that it's mostly found in Central and Southern America. And there the plant is actually seen as almost like a weed, like the weeds you see outside, like something you want to get rid of, because they just have it everywhere, everyone in South America. And it's almost seen as a nuisance. And here in America, it's actually different. It's almost treated as a royalty, because they have these plants like in high-end stores. They have it and greenhouses, and they sell it pretty expensive for just being a simple plant, but it just shows that that one phrase that's one man's trash is another man's treasure, because here in America, it's very rare to get your hands on it. We got it at this one store in Atlanta, but it's it just shows that how special this plant is when other people just think it's just trash, but um, it's actually located in Georgia in small places. It's actually in Marietta. You can find it in the Golden Branch Trail or the Vickery Trail. And yeah, just don't go poking around like every single plant, but you sort of see like this little fern, it might be that plant. And if you want to purchase it, I actually got it at in Roswell. It was at the J Tree Garden. Um, I called up to them because I was trying to get a new one to demonstrate to you guys, because I accidentally drowned ours, because they're actually not supposed to receive that much water. The soil is actually supposed to be pretty dry, and every time I saw the plant dry, I was like, oh, it's dying. So I just kept refilling it with water, and it's ended up drowning it. But if you guys want to get your hands on one, you can go to Jade's Garden, and I'm pretty sure they'll have it there. Is there any questions about the plant?
Did
If
they?
not,
I have one question. Did they grow very heartily in near your home? Was it a dry climate at your home?
it's not that it was a dry climate. It's sort of that we just have so much plants. Sometimes you get confused about what's required of them. We have like I just had in my backyard. We always plant um, flowers. I actually have like something right here across from me, just a big plant. And you sort of get confused about what's required of them. And for this one, it's not supposed to have a lot of water. I didn't really know that, because I didn't really know the name, because I lost the little thing that they put in the plants. But it's not that hard. You just have to be careful, because they tend to have these little white, it's almost like mites, almost not mites, but these little insects. And we actually had a couple problems with that. And what you're supposed to do is just like flush it out with water, and for a couple of times for 1 week, and that is what gets it off. But it's not really that hard to maintain. You just have to not drown it, not put too much water on it. The soil is supposed to be pretty dry, which I guess sort of makes sense why it's in South America, because I guess the heat, it makes the soil dry instead of it being moist. But yeah, it's mostly found in South America.
Hmm.
It's not really found here, and there's like so much of it. I was like looking at pictures, and like people actually like just get rid of it and just cut it off, because they don't like it. It's just too much of it. And here it's only found in the high end places. You know, makes that plant special here, because
Hmm.
it's just about its little trick that it does. But yeah, if there's no more questions, that's the end of my presentation.
Hi, everybody. My name is Valina Spencer. I'm going to do my everyday phenomenon today. And first, I want to start out with uh, the standard that I'm going to use. And our standard today, because I teach earth science, is S6E2 to obtain, evaluate, and communicate information about the effects of relative positions of the sun, earth, and the moon. And A is using a model to demonstrate the phases of the moon by showing the relative positions of the earth and the sun and the moon. And I wanted to ask you guys some questions. So we're going to use our prior knowledge to ask you, what do you see in the sky at night? So if you could give me some answers on that.
Clouds.
At night, okay, you do see clouds at night. And what else?
Stars.
Very good.
The moon.
Yes, we do. We do. Very good, guys. And what do we see in the sky during the day?
Clouds.
All kinds of different clouds. The cumulus clouds, the other ones that give us weather. It could be fog or whatnot. What else do we see in the sky during the day?
We also see the sun.
Yep, that's perfect. We do see the sun. Yes. So those are things that we're going to be looking at here. And some of our vocabulary that we'll talk about are the first quarter moons, full moon. I'm not. I want to share my screen. And the last quarter moon, the lunar cycle, and the new moon, and when the moon is waning and waxing. Yes. So our focus here is the moon, and I wanted you to see that my phenomena, my everyday phenomena, is centered around why do we see the moon during the day sometimes? Because I think that's interesting that we all said that the moon is definitely up at night, but there are times where we see it during the day. So we're going to examine that as our everyday phenomenon. Now, we have to look at the fact that sometimes the moon appears, you're not able to see it when there are clouds, and it has to be the right time of day, and if the sun washes it out. But we're going to go through and we can look at the phases of the moon, and that'll teach us then how to see when the moon is able to be seen during the day. So the moon goes through phases because the moon is rotating around the earth. It is tidally locked, so we do see it only in one position. As we look at the phases of the moon, we see different quarters of how it goes. So the moon has a full cycle from new moon to new moon of 29.5 days, and the moon goes around the sun in those 29.5 days. Now, half of the time the moon is able to be seen during the day, and half of the time it's only being able to see during the night. And what we're going to do is to examine how which days are we're able to see the moon in the daylight. We'll go through a different crescent moons. The moon goes through different phases, as we saw in our first slide. At first, we go from the new moon now to the waxing crescent. This means that the sunlight is starting to illuminate the moon in a certain phase. So it's a crescent moon at first. And as we call it waxing, it's like you're putting wax on. We like to teach that when you're putting wax on, that's how you know that it's coming where we're able to see the sun the moon illuminated by the sun during this cycle. The next is the first quarter moon. The first quarter moon is 90 degrees away from the sun. And we call it the first quarter because the moon has traveled about a quarter away around the earth. Next is the waxing gibbous. Waxing gibbous is
So hello everybody. So today in class we're going to be learning how a remote control essentially works. All right. So quick question. Have you ever stopped to wonder how the remote control work, or how come your TV remote doesn't trigger maybe back in the day if you had a video player? And why do you always have to point the remote directly at the TV? Has anybody ever considered that?
Yes.
Yeah.
Yes, sir.
Okay, awesome. So today we'll be going pretty much in depth, and my goal is by the end of class today, we would have answered all three of these questions. All right. So first things first, what's important for us to know is that remote controls use infrared beams. So whenever we're using a remote, it's pretty much sending a signal to whatever needs to be controlled. Electromagnetic waves. Now, you may be wondering what are these electromagnetic waves? Well, some examples of electromagnetic waves include light, X-rays, radio waves, microwaves, etc. All these are examples of electromagnetic waves. Bluetooth is also included in there, and also Wi-Fi. All right. So I'm not sure if you all have a remote with you, but let's just assume, we have our trusty remote right here. So first thing I want you to do is take a look at the top of your remote. Whenever you take a look at your remote, you'll notice that it has uh, a small little bulb that's housed at the very tip of the light. It's sort of in the direction where you would be pointing towards the TV. This small little piece of plastic is known as an LED. This LED stands for a light emitting diode. So this little small plastic is where our infrared radiation comes out of. All right, so now I've just asked you to look at your remote. Now take a look at your TV, your video player, your Wi-Fi connector, anything of the sort. If you do, well, not if you do, when you do take a look at that, you'll notice that somewhere on the front that there's also a very small plastic that's housed at the front of the TV or front of the item in question. This is where the TV receives the information that is being sent from the remote. So whenever you press a remote control to do a function, like let's say maybe you're turning up the volume, a beam of infrared radiation travels from the remote to the TV. Now, I know some of you all may be wondering, well, hold on, Mr. Fishola, I've never saw a light traveling from my remote into my TV. Well, the reason you may have never seen this is because this light travels, or excuse me, this infrared beam travels at the speed of light. All right. And another reason you may have never seen this phenomenon occurring before is because our eyes, and by our, I mean humans, human eyes aren't particularly sensitive to that type of light. All right. And if you take a look at the remote here, this essentially gives you a visual of what you can expect. Not so much as what you can expect, but this gives you a visual of essentially what the whole process looks like. So the remote being housed right here, we know we have our small LED plastic being housed on the front of the remote, and it's going to send this electromagnetic infrared beam towards the TV, video player, whatever we're attempting to control. All right. So in the previous slide, you may have noticed that I said that human eyes cannot detect. I'm sorry for that. Okay, so let's say you decide to conduct a personal and you attempt to change the channel while staring hard into the remote to see if you would see an infrared beam coming out of your remote. So even if you were to conduct this experiment, it would be unsuccessful because, like I said in the previous slides, human eyes are not sensitive enough to detect this infrared beam. So only certain animals possess this power. Animals such as rattlesnakes, raccoons, mice, and etc. can see infrared beams. Humans have made advances in this, well, not so much as in this field, but have made advances to be able to see infrared beams, but through the use of special goggles. But this is a skill that we do not have on our own. All right. So so far I've spoke on the infrared beam, the LED that's being housed on the remote, the infrared beam that the LED makes and sends it to the TV, but that's still not really quite explaining what's really going on here. So essentially, when we click our remote to make our TV do a command or operation, what happens is this infrared beam that travels from the remote to the TV houses, not really houses, but it's essentially the catalyst for a sort of binary code, which gives the TV different instructions in different directions on the operation to perform. So essentially what binary code is essentially a language using only ones and zeros. And the ones or zeros are organized in certain patterns to where they mean different things. So a short pulse of infrared signal from our remote to our TV can land either between 1 and 0, or 0 and 1, or 1 and 1, or essentially there are infinite possibilities. All right, but these patterns in binary code that occur are essentially what gives us our function on the TV. So I attempted to break that down a bit more, just to sort of give an example. So let's take a code. Essentially, not essentially, an example is 101101. Now, this particular set of binary code could mean volume up, while another set, such as 1111011, could mean mute sound. This could also work in reverse, where essentially the same code backwards could mean unmute, or the same code backwards could mean volume down. So another aspect of this phenomenon is that the remote also sends a short code, not really a short code, but it's sort of a special code. And the specialness of the code is so that the remote performs the correct operation on the correct device. So essentially, not essentially, but this code contains information such as the make and the model of the TV, and essentially this is what prevents us from cutting off our PlayStation with our TV remote. All right. So and here's a bit of an extension to the topic. So if there were some way where we could discover, let's just say, the code for every remote operated system on Earth, we would essentially be able to make that piece of technology do our bidding if there was a way we could discover all the codes. So, and this essentially is how universal remotes work. Universal remotes house a wide database of binary code and a specific binary code that is relevant and related to the make and the model of the specific appliance that we want to work. So essentially that's how universal remotes work. They just have a very large database full of information that can get whatever we need to get done. All right, so that's it for my presentation. Does anybody have any questions?
I have a question.
All right.
So, are these same binary codes that computers would use?
Yeah, that was a great question, Valina. Thank you for asking. And yes, these specifically are the exact same binary codes that computers and certain programmers do use in their work. So that was an outstanding question, Valina.
Okay. And sometimes, I have a remote control that surprisingly controls like a TV and a Fire Stick. So, so could you explain a little bit of how that worked?
Mm-hmm. And that's an outstanding question, actually, Valina. So I actually have the same experience with my TV and my remote. My remote controls my Fire Stick. It controls the Fire Stick and the TV essentially at the same time. So I believe what's going on here is that the specific TV and the specific, well, not really the specific remote, but specifically the make and the model of the TV, the makers essentially encrypted with information like that to where the remote would be able to read and operate directions from whatever is plugged in through the USB. Because what I've actually also noticed through, not through, but with my TV, is that whenever I cut on my PlayStation, I could have the channel on. I could have the channel on the HDMI where my Fire Stick is on, so I'm watching TV there. But whenever I cut on my PlayStation, I notice that the TV automatically goes into the HDMI port, which my PlayStation USB is housed. So I would say that's something specific to the make and the model of the TV and something they personally encrypt into it.
I think it's good that they do that because, it keeps down the amount of remotes that you have.
No, I definitely agree. And I love this TV because it does that. So I definitely agree.
That's good. I did always want to know how the remotes worked. And the universal ones can be hard to program. Are you able to program those, Ms. Priscilla?
I can, but not without hours of frustration. But we can make it happen.
Okay. Hoping you can help me out.
All right. Well, if there are no more questions, that's the end of my micro teaching.
All right, y'all. So right now I'm going to teach y'all about some science and cooking. And my name is Francisco Gracia. Yes. All right. So we're going to go through this through cooking an egg. Okay. So the first thing is cracking an egg. Okay. So why do y'all think that eggs crack?
They have a hard shell made of calcium.
Dami, you're about to say something too?
Yeah, the pressure being applied to it.
Yeah, so there's more force being put upon the egg than it can handle. So when there's forces, when there's a force, there's an opposite an equal and opposite force back at it. So the egg doesn't have enough integrity to hold on to that force. So it breaks and cracks. So when we crack an egg, is this a physical or chemical change?
Physical, right?
So,
Everyone agrees it's physical. Why do y'all think it's physical and not chemical?
He's putting force.
force.
Yeah.
Yeah, and physical changes, we still have the same object, right? And when there's a chemical change, it's turned into something different. So like if you have a piece of paper and you cut the paper, then that's a physical change. But if you have the same paper and then you burn it, then it becomes a chemical change because it's no longer paper, now it's ash. Okay? So then next we're going to put the egg inside the bowl and we're going to scramble it, okay? Is that a physical or a chemical change?
Still physical because you're just whipping it.
And you still
Right,
have
and
the same substance.
yeah, it's still the same substance, and it's still just a raw egg. Okay. And is this mixture homogeneous or heterogeneous?
Homo.
Homogeneous. And then what is Steve and Valina think?
Uh,
I'm gonna say hetero.
Hetero. And Steve?
I think hetero as well.
Yeah, so when I was thinking about this, I was thinking it was a heterogeneous also. Because well, if you like whipping it there for a long, long time, you could still see some different parts like of the yolk and the white part of the egg. So I was thinking it was hetero, but some people would think it was homogeneous because it looks like one equal mixture. But yeah. All right. So next we're gonna get the stove ready. Okay. So there's two different types of stoves. Well, two different stoves I wrote in here. So we got the gas stove top and then an electric stove top. All right. So who thinks they can explain how a gas stove top works?
Uh, I think I could give it a shot.
Yeah, go for it. Let's see what you got.
All right. So when you cut on the gas, the propane or whatever gas is coming through, and there's some kind of igniter that's that clicking sound you hear,
Hmm.
and
Yeah, exactly. So it's a combustion reaction. So a combustion reaction is basically it's a reaction that gives you fire when oxygen and the propane mix together, and then the spark lights them both up, and then it comes into a controlled flame with the stove. And then anyone want to try explaining an electric stove top?
The electric stove top has a heating element, and it uses electricity, and it somehow begins to make the heat within the element that's there.
Yeah, exactly. So with the electric stove tops, all that's happening is that it's converting the electricity into heat energy, and then that's when it starts heating up the coils inside of it, because there's some coils that get heated up through the electricity. All right. So now we're gonna start up a little bit. So now we're gonna put the pan on the stove, right? So who knows how the pan heats up? Let's just say we're doing a gas stove top right now. So when you put the pan onto the stove,
Oh, I
and
think
oh, go for it, Evelina. I'm sorry.
I want to at least say that the molecules speed up
Yep,
and,
exactly.
and they
So,
heat up the pan.
hmm so when you put the pan onto the stove, right? The flame is there, and the flame is leaving off it's radiation. So the pan is heating up, and the molecules get excited, and they start moving faster, and then it starts becoming hot. So then next I'm cooking my eggs with butter. I don't know how y'all cook y'all's eggs, okay? But right here we're cooking with butter.
So come with
Okay,
butter.
so
Add some salt on there too.
yeah, so we're gonna put some butter in the pan, okay? So the butter heats up through conduction because it's touching the pan directly, and the pan's already hot, right? So the heat from the pan is being transferred from the pan into the butter, and it's heating it up, making it melt. So it's converting from a solid to a liquid because we use putting a butter stick on there. All right. So next, let me see. Yeah. Okay. So next we're gonna start cooking the egg, and then you pour the egg into the pan, and the egg flows. Oh, hang on, I had another question on this other one. I forgot to ask. Yeah. So when the butter is changes from a solid to a liquid, is it a physical or a chemical change?
physical.
It says physical. Alina and Steve, what do y'all think?
That is a Physical. I'm gonna go with physical.
And what was physical too?
Right, it's a physical change when we're just heating it up. Well, that's if you don't burn the butter, okay?
Right.
If the butter gets burnt, then it becomes a
Yeah.
chemical change because you can't unburn the butter. But when it's if you melt it correctly and it doesn't burn, then you could just pop that back in the fridge and it'll become a solid again. All right, so now we're gonna cook the egg. So we're gonna pour the egg into the pan, and then the egg flows because we know, we mixed it up in the bowl, right? So when you're pouring the egg into the pan, the egg is flowing down due to gravity. 9.8 meters per second squared. Y'all know gravity. Gravity is awesome. And then the egg is heated and cooks. So the egg is heated up through the what was it? I'm sorry. Through touching of the butter. And then so is the egg being cooked a physical or chemical change?
Chemical.
Chemical, yeah.
Chemical.
Right, it's a chemical change. Okay, does anyone have any questions?
I was thinking something about the. Could you go back a couple slides? I think it was like slide 3.
Oh, yes, sir. Let me see. Oh, why is not my bad? My B. Slide 3. Yes, sir. What's up?
With combustion reactions, because I have this thing at work. Is like.
The flame torch.
Yeah. To actually start the flame torch, you have to have some tool to like.
Yeah, I know.
click,
That's
yeah.
like the metal clips, and then you squeeze it and it leaves a little spark.
This
Would that also be that?
Yeah, that's the same way the stove works, because it's releasing the gas and then the spark ignites, making it go on fire. And I'm not sure exactly how it releases it like precisely. I think it's like
It's like sparks almost when you squeeze the actual thing like
I
Yeah.
something
think
like that.
it's a flint. It's like a flint thing, a tool that they use in the labs that provides a spark. And so if you got gas around, it's gonna make it, go. That's why you don't want gas in your house and then you light, a candle and then everything explodes because it's combustible. Yeah,
Right.
it's combustible.
Any more questions? No, we're good.
So can you explain a little bit about the why is it a chemical change when you cook the eggs?
Okay, so when you're cooking an egg, it when you put the raw egg in and then you come out with a cooked egg, you can't go back to a raw egg, right?
That's right. I know that. Mm-hmm.
Right. So the egg is cooked. I'm not sure exactly what happens with the molecules inside of it, but you can't convert it back, and it's still an egg, but it's like a different substance.
Okay.
You get what I'm saying?
I do.
Yeah.
So whenever something loses its original property, it's always going to be a chemical change, or is there other special cases where it's a physical change? I'm trying to
Yeah. So
think.
usually when it loses its properties, it's going to be considered a chemical change, since it's becoming a whole different item and object.
Okay, I got it. So something like fireworks would be considered chemical.
Right. So like if you're lighting a firework, so a firework is just powder inside, right?
Yeah.
So then once it's lit up and it explodes, the powder is not there anymore. The powder converted into the light. So yeah, that would be a chemical change.
Okay.
All right. Let me see. All right. There's no more questions. That's and my presentation. Thank y'all for coming out. I appreciate y'all.